All right, this is Honors Algebra 2 Pre-Calculus. We're doing 6.1 in Algebra 2, which is exponential growth and decay. So a really common application or example of exponential growth is when we talk about bacteria. So bacteria are very small single-celled organisms that live almost everywhere. Most bacteria are not harmful. In fact, you eat a bunch of them in things like yogurt. But bacteria reproduce or grow by dividing, right? So the total number of bacteria in a given time is referred to as the population. When each bacterium in a population, bacterium is the singular, we just usually say bacteria because they're generally a bunch of them, divides, the population doubles. So you can see what's happening here is you have a population of, let's say, 100, right? That's the total amount of bacteria at the beginning. And after an hour, 1 hour passes and the population doubles because each one of those individual bacterium divides in half, creating 2 bacteria, right? And that keeps happening. So this is an example of exponential growth. So you'll see this formula right here, right? This 100 times a 2 to the n, right? So in this situation, and we're going to spend a lot of time doing this in this chapter, but the 100 is the starting population, right? So we'll often hear that as an initial population, right? This is the starting population. And the 2 is because this quantity doubles every hour, right? That's why it's a 2, because it doubles. So we're going to spend some time talking about exponential growth and decay in this section. All right, so the population after n hours can be represented, as we just saw, by 100, which was the starting value, and then a 2 n times, because you're multiplying by 2 each hour, and there were n hours, so 2 times 2 times 2 times 2 n times, which would be a 100 times 2 to the n. So this expression is called exponential because the exponent is a variable, right? So that's what makes the expression exponential. And the base can often be called the multiplier, right? Because I'm multiplying by that base, that 2, every single time. So the expression a times b to the x, b is called the base or multiplier, and a is the initial value when x is 0. If this b is greater than 1, then what's happening is we have exponential growth, and we're going to spend a lot of time with that. So that's what we just saw, right? The bacteria population is growing, right? If b is between 0 and 1, we have what's called exponential decay, which would mean the population or the quantity is decreasing exponentially. So on the next slide, we're going to go over how to find these multipliers when you're given a particular word problem situation. And again, we're going to spend this entire chapter on exponential stuff and logarithmic stuff, so don't panic if this seems like a lot. All right, so the multiplier or base for exponential growth or decay, well, so here's the logic, right? So the current amount of something is 100%, right? Which as a decimal is written just as 1, right? So if the quantity is growing by 20%, then the new amount will be the existing 100% plus the other 20% that you gained, thus 1.20, right? That would be the multiplier. So if something's growing, right, it's 1, which is the amount you currently have, right, plus the new amount because you're gaining that amount, hence the 1.20, right? If something is decaying, which means losing an amount, right? If something's decaying by 20%, then it would be the current amount you have, which is 1, because that's 100%, minus the amount that you're losing. So your multiplier would be 0.8, right? So we're going to go ahead and walk through 2 examples where you find some multipliers. So find the multiplier for each situation. So notice that this is growth, right? So because it's growth, I'm going to take the 1, I'm going to add to it the amount I'm gaining, which is 0.25, right? So again, the 1 is what I have, the 0.25 is what I'm gaining, so the multiplier is going to be a 1.25, right? 7% growth, right, is going to be 1, that's what I have, plus the 0.07, which is what I'm gaining, so the multiplier would be 1.07. Now this one's decay, so that's going to be the amount I have, which is 100% minus the 0.16, so I'm going to get a 0.84 as my multiplier. And 3.5% decay means that I'm going to have the 1 minus 0.035, good times, which should be a 0.965. And that's how my decay works. So you're going to go ahead and try that in a P1. All right, give it a try. Pause me if you want. So 18.5% growth is going to be a 1 plus a 0.185, which is going to be a 1.185. Right, and it's plus because it's growth, right? 100% growth is going to be 1 plus a 1, which is a 2. So that's actually the situation that we saw. The other way to say 100% growth is something doubles. Right? So we saw that with the bacteria at the beginning. 100% growth is the same thing as saying you double because you gain 100% of what you currently had, meaning you double your amount. 12% decay is going to be a 1 minus 0.12, right, which should be a 0.88. Right? And 4% decay should be a 1 minus a 0.04, which should be a 0.96. All right, moving on. All right, so for example 2, we're going to go ahead and do a word problem. So human populations grow much more slowly than bacteria populations. So we've seen that bacteria populations generally double in an hour, which would be crazy if that's what human populations did. So we're going to look at a human population starting in 1990 and then kind of compare it to other values. So the population of the United States was this giant number in 1990 and was projected to grow at a rate of about 8% per decade. Now that's going to matter that it's not per year, so we'll talk about that in a sec. We're going to use this information to predict the population to the nearest 100,000, which is not a decimal value because it's weird to predict decimal people, for the years 2010, which we could actually check against the real statistical information, and 2025, which we're getting darn close to. So in order to do this, I need some information. First thing is I'm going to call P of T the population. Okay, I'm going to call T decades since 1990. Okay, so the reason I picked decades is because the population is growing at 8% per decade, not per year. The reason I started in 1990 is that's when my initial value is. So T equals 0 is 1990, right? All right, so the way this is going to look, I'm going to get that the population with respect to time, so P of T, is going to be this crazy, giant, huge number. All right, this number, times my multiplier. Well, I'm growing 8, so it's a growth rate of 8% per decade. So my multiplier is 1.08 because it's the 100% of the population that exists plus the 0.8 that I'm gaining for the 8%. So 1.08, and then T, my exponent is T in decades, right? So what I'm being asked to find is I'm being asked to find 2010. Well, 2010 is 2 decades after 1990, right? It's 20 years, that's 2 decades. So I'm going to type in 248718301 and then 108 to the second, right? And then 2025 is 35 years since 1990, so that's going to be 3.5 decades, which is going to mean I type in exactly the same thing, except I change that exponent to a 3.5. Cool. All right, and then we're going to get an approximate value. So let's go ahead and type that in. So be careful typing. It's really easy to accidentally type the wrong number. I've done it myself more than once. All right, so 248,718,301, and then double check that with what the original actually said so that you just make sure you didn't miscopy that. Okay, so then I'm going to do 1.08 to the second and hit enter. Okay, and then I'm going to hit second, enter, and change the second to a 3.5 because that's going to mean that I have both answers in one screenshot. So let's go ahead and grab a quick screenshot of those. All right, and bring it over here. Okay, so we'll put those right here. Okay, kind of lazy of me, but that's all right. Cool. So those are my two values. Now notice that here you were asked, normally I say round to the thousandth place, but here it makes more sense to round to entire people, and more specifically, the reason they're asking you to round to the nearest 100,000 is because in terms of the accuracy of this model, it's probably not accurate to like down to the person, right? So if we round to the nearest 100,000, you can see if I put little commas there, right? So to the nearest 100,000, we're looking at this 6, and to the nearest 100,000, we're looking at this 1. So, so in 2010, we're looking at 290,100,000, right? And in 2025, we'd be looking at approximately, and we're going to just go ahead and say people, 325, 600,000 people. Okay, and there you have it. All right, so moving on. All right, so give the same concept a try. This time you're talking about population of Brazil in 1996, and we're talking about a growth of 7.7% per decade. So again, notice that this is your year 0. You want to start in 1996. All right, And then actually we could compare both of these statistics to the reality of the world because it's already 2020. So give it a try. I'm going to go ahead and call P of t the population. Right? I'm going to call T decades since 1996, which for the record means that t equals 0 in 1996. That's the whole goal, right? So my formula is going to be P of t equals the starting value times my multiplier. Well, my multiplier, since this is a growth rate of 7.7%, my multiplier is going to be 1.077, right? And then raised to the number of decades. So in 2016, right, that's 20 years, right? 20 years is 2 decades, so that's P of 2, which is going to be 1.077 to the second, and then I'm going to get in a value. And then if we do 2020, right, so that's 24 years, right? It's 24 years, so that's 2.4 decades. So that'd be P of 2.4, which is the same exact thing, but you're going to change the exponent of 2 to a 2.4. Right, so that's the goal. All right, so again, once you type it once, you shouldn't have to type it twice. So you do 162.661.000. You should double, triple check. All good. 1.077 to the second, right? And then I'm going to hit second enter, and then I'm going to change it to a 2.4, right? There's no reason to do all that work of entering it twice. That would just be silly, right? We want to work hard for sure, but we also want to work smart, right? It's important to do both of those things. Cool, so I just kind of cheated and cut that and pasted that into here, so that's those two values. So my answer, right, if I squeeze my answer in here, is in 2016, we're looking at approximately, and they did say nearest 100,000 again, so this would be what I'm rounding to here, and this would be what I'm rounding to here. So 188,700,000 people, because it rounded. And in 2020, we would be looking at approximately 194. That would round to a 400,000 people. All right, moving on. Okay, so modeling biological decay. Okay, so caffeine is eliminated from the body of a child at a rate of about 25% per hour. The exponential decrease in caffeine in the child's bloodstream is shown in this chart. So the rate at which caffeine is eliminated from the bloodstream in an adult is about 15% per hour. An adult drinks a caffeinated soda, and the caffeine in his or her bloodstream reaches a peak level of 30 milligrams. Predict the amount to the nearest tenth of a milligram of caffeine remaining 1 hour after the peak level and 4 hours after the peak level. Okay, so the peak is at the start of this problem, is 30 milligrams. So that's our starting value, right? So I'm going to use, we go ahead and say C of T is the amount of caffeine in the bloodstream, right? So amount of caffeine in the bloodstream. I'm going to say T is time in hours since that peak, right? So meaning T equals 0 is the peak, right? So the caffeine in the bloodstream is going to be the starting amount, which is 30, right? And then we're decaying, right? So this 15% is decay, right? We're losing caffeine, not gaining caffeine. So the decay is going to be a 1 minus the 0.15, meaning that my multiplier is 85. One way to think about this is that if you're losing 15% of your caffeine, you are retaining 85% of your caffeine. So once I have that formula, right, what they're asking me to find is they're asking me to find C of 1, right, which will be a 30 times a 0.85, which we can approximate in a second, right, and that's going to be milligrams. And they're asking me to find C of 4, which is going to be a 30 times a 0.85 to the fourth, which again we can approximate, and it will be in milligrams, right? So let's go ahead and find both of those values, right? So we have 30, and then this is a 0.85 to the first, right, which I don't have to write. I could just write 0.85, but I'm going to write to the first so that I can be lazy, and in a second I can change that to a 4. I don't know whether it's lazy or not, but there we have it. So if I put both of these in here, and I know I could just copy them, but again, I'm going to go ahead and take advantage of our screenshot abilities. Right, so let's drag this guy down here, drag this guy over here. All right, so they specifically in this case told me to approximate to the nearest, they told me to approximate to the nearest tenth, right? So you do want to pay attention to what the instructions say. So tenth, right? So this one actually is a 2.55, and you can get rid of the approximation because that when you're not rounding. But for this one, when you round, you could either, since it doesn't, it does say to the nearest, so that usually means rounding, so they want you to round this to here. I personally don't care if you round or truncate. I'm a fan of doing either, right? So there we have it. All right, moving on. A vitamin is eliminated from the bloodstream at a rate of about 20% per hour. The vitamin reaches its peak level of 300 milligrams. Predict the amount to the nearest tenth of a milligram after 2 hours after the peak and 7 hours after the peak. So again, what we're looking at is, because it says eliminated at 20%, right? What we're looking at is we're looking at decay, right? So 1 minus 0.2 would give me a 0.8 as my multiplier, right? We know the peak amount is 300. So let's say V of T is the amount of vitamin, right? And we're going to say that T is hours since the peak level, right? So the point here is that T is 0 is at the 300, right? So my V of T is going to be 300 times 0.8 raised to the T, which means the two things I'm being asked to find are V of 2, which would be 300 times 0.8 to the second, and V of 7, which would be 300 times 0.8 to the seventh. And again, we're going to use our calculator to find both of those things. So we're going to do 300 times 0.8 to the second. And then we're going to hit second enter, and we're going to do the same thing with a 7. Again, there's no reason to make your life harder. So there's both of my values. All right. Cool. So I was asked to approximate both of these to the nearest tenth, right? So here I don't have to approximate. It's 192. It was measured in milligrams, right? And V of 7 is going to be 62.9 milligrams, right? So this is 2 hours after the peak. This is 7 hours after the peak. All right, moving on. All right, so just a little bit of practice at typing this stuff in. We're just going to evaluate each one of these at x equals 2 using a calculator. So this would be 3 times a 5 to the second. Now, honestly, if you want to do this one, so you could do this one by hand. This is definitely a 3 times a 25. So if you just want to get that as a 75, great, right? This is a 0.7 raised to the 2 times 2. So you're going to type in your calculator 0.7 to the fourth, and you're going to get a value, which we'll do in a sec. And this is a 100 times a 0.85 to the second, which, again, you're going to type in your calculator and get an answer. So the goal here is just to make sure you know how to type it in your calculator. If you wanted to make sure you know how to type the 3 times the 5, you could do this, right, and double check that it is a 75, but it is. Here you've got a 0.7 to the fourth, right, and here we have a 100 times a 0.85 to the second, and there we have it. So we put, again, the goal here is just to make sure that you know how to put stuff in your calculator, because it is important that you can enter things in your calculator. All right, so we're going to get that this is approximately a 0.240, and because, again, we usually go to thousands places, and that this is a 72.25. All right, and actually we could just put equals here, and actually if you wanted to just say equal, this is a, you don't have to round this. So this is approximate, this is actually equal, right? All right. You're going to try the same thing with x equals 3, right? So go ahead, and again, the goal here is just to get you some practice entering this into your calculator. If you're putting this in your calculator, you're doing something akin to this, right? This is a 0.62 caret -6, right? Right, and this is going to be an 80 parentheses 0.5 caret 3, and then you get a value. All right, so again, the goal here is just to make sure you know how to put stuff in your calculator, right? So 12 times a 5 to the third, 0.62 to the -6th, and 80 times this 0.5 to the third. Right, so this one comes out to be, and I don't need the approximate because it's actually equal. It's a terminating decimal, right? Oh, I'm sorry, that's the wrong spot. I copied the wrong one. What was I thinking? I still don't need the approximately. It's definitely still equal. It's the 15, my bad. This is a 17.605 or 6, and I definitely need the approximately because this is an approximation, and this one just comes out to be a 10, which again doesn't need the approximate because it's actually straight up a 10. All right, and that is it for our first video.